Well, I'd actually like to start by thanking Boris because Alan Kay has always been bragging in his talks about how Squeak had a mathematical model that allowed it to run everywhere. So now it's becoming true. I'm actually going to talk about rather old technology. It's 25 years old now, but it's new to many people, and that's called adaptive compilation. And I'm going to take Julie Andrews' advice and start from the very beginning. If you didn't get that, then lucky you. So we have computer science, that's what we're talking about, but there's the opinion that computer science is not about computers. So what is it about? It's about process. Perhaps we should call it process science instead. And what is a process? A process is something that will take something that you have and it will give you something that you want. So you can have a mechanical process, you can have a biological process, chemical process, and you can have computing processes, which is what we're going to be worried about. I'm going to define a problem. If you have something that you have and something that you want, then that's a problem. So there are many problems in the world. And for a given problem, there might be several different processes that will solve that problem. And for a given process, we can have several computational models in which I can describe this process. For example, there's something called finite state machines where only one of these little circles is active at one point, and then it transitions through the arrow to another one. There's Petri nets that are easier to describe, processes where several things happen at the same time. I can take a bunch of NAND gates, which are little logic circuits and wires, and connect them together. That's a computational model that can be used to implement a process. So now I said that for a given problem, there might be several processes that solve it. So curious minds want to know, are there any problems for which there are no processes that can solve it? And a curious mind, for example, was Alan Turing. 1936, he addressed this problem. It was a paper that obviously you're not going to be able to read there, but it's available online if you're interested in, and I really suggest it because a lot of people just read about the paper and get some weird ideas. So he had to have a computational model in which to explore this problem, so he created something that is now called the Turing machine, which is basically the finite state machine that we already saw, but he adds an infinite tape of which you have a head that can look at what's written on that position of the tape, and it can go to the left, can go to the right, and it can replace what's exactly under the head. And that's controlled by that finite state machine. But using our abstraction, let's imagine that we have a Turing machine that implements the check A process, which I have no idea what that does. And it will take, on the left, the little reddish-brown thing is the input tape, and then I get the output, the green tape. In the case of the Turing machine, it's actually the same tape that has been modified, but we think about it like this. It has an input and gives me an output, and the computational model that I'm using is the Turing machine, TM. And it was interesting that in his paper, he thought about, could I implement a Turing machine that would take another Turing machine as its input, and he called this the universal Turing machine. So it takes a Turing machine, the yellow one, and its input tape, and it produces the output tape that it would have done it. So how is that how can it input another Turing machine? You can encode it on the tape. The tape is infinite, so if I add 5,000 cells to it so that I can somehow encode the yellow Turing machine, well, it's still infinite anyway. So that's the great thing about mathematics versus engineering, right? We don't get infinite tapes. So this, I'm saying that I implemented a simulation of that Turing machine. And when we're simulating a language, we normally use the term interpreter. So what happened was, the same year, another guy, Alonzo Church, he explored the same question using, or related questions, using a different computational model that we call lambda calculus, which was the inspiration for the Lisp programming language. So now you had these two computational models, and they were exploring the problems. Which problems do they solve? Which problems don't they solve? And they got together and they decided that they both solved the exact same set of problems. So they were equivalent in some sense. And in fact, any computer that you can think of in the future, if it's powerful enough and the threshold is very low, then it will solve the same set of problems. And unfortunately, this thing has caused a lot of grief in computing. So Alan Perlis says for you to beware of the Turing tar pit, where just because, so all computational models are equally equivalent, so I'll choose any one of them. Let me just give you an example with the simulation, the interpreter. So this combination gives you the exact same result as just the yellow Turing machine would, right? So they're equally valid. Well, you have to remember that the simulated Turing machine will take a bunch of steps, maybe 100 steps, for every one step that the yellow Turing machine would have taken. So they're only equivalent if time doesn't mean anything to you. So if it's 100 times slower and you don't care about that, then they're equivalent. And I could also do that check A as a finite state machine. It's simpler. I don't even need the tape, right? So why don't I prefer a finite state machine? Well, maybe check A is implemented with just 6 states in the Turing machine, but would take almost 1 billion states when implemented as a finite state machine. So if memory doesn't matter to you, then they're equivalent, right? So, but what's interesting about having one kind of machine, here the Turing machine, a universal Turing machine is simulating another Turing machine, but there's no reason why the Turing machine, I couldn't build a Turing machine that would simulate lambda calculus. And if I did, then, well, now I can see that they're equivalent. And the same thing, I could use lambda calculus to implement a simulation for a Turing machine. And then that proves that they're equivalent. But a very practical way, if you have a solution that's in one computational model and you really want another one, is to have a translator. That's often called the compiler. So imagine that I write a program using the Python computational model, and the process is the compiler, and it will take check A as described in lambda calculus, and will produce check A as described in Turing machine. And now I can execute the Turing machine. So this is a two-step process. So compilation is more complicated than simulation interpreter. But it will give you results because now the compiled Turing machine is as fast as the original lambda calculus. It's not 100 times slower or something like that. So, and the reason why it's called compiler is because the first translators, they just had a simple dictionary of source instruction and destination target instructions, and it would compile. Compile is to gather together lots of information. It would compile these code fragments into a larger program. I don't like the word very much, but we're stuck with it. And I can also have a hybrid system, which is what we've been seeing here, where if I have a sieve process written in Smalltalk 80, and I have a compiler written in bytecodes, then I can generate the sieve in bytecodes. Now that I have the sieve in bytecodes in some input, then I can have a VM that's, the virtual machine is a process written in x86 machine language, and it will produce, it's running on an actual physical process. You have this tower, eventually you have to get to actual physical hardware, or else you don't actually have running code. So it will produce the result. So actually this picture isn't correct, because you can't have the compiler bytecodes loose like that. Let's put it on a virtual machine like that as well. So that's actually what's going on in Squeak. So you type the sieve in Smalltalk 80, and eventually you get code that writes. So that's the simple that what we normally say, oh, this is the Smalltalk interpreter. That's the structure of the Smalltalk interpreter. Now I'm going to quickly go through these examples where I'm going to show some code that's in red, that's variable. And some code that's in blue, that's constants. So what happens when you have a mix of variables and constants, and it's always 3? Well, that's even simpler. I don't need to generate the code to calculate. In fact, if I say that it's static, then this is placed in a known, the variable v now lives in a known position in memory. It doesn't change every time I execute, so the compiler can just put its address, 28F0 whatever, and that. In fact, maybe the contents of v is known. And in that case, I just load 2.5 into register 1, and I'm done. So the more constant that I have, the better the code that I can generate. And so some languages have lots and lots of constants, like Fortran. So we call them static languages. And they make it very easy for you to generate a very simple compiler. While other languages, like Smalltalk, something that we're proud of Smalltalk, is what we call late binding. Decisions are made as late as possible. And that that means variables. And so your compiler will generate these, has to generate lots and lots of code for these variables. At some point, you're actually generating almost the whole interpreter. So you might as well just use an interpreter for these dynamic languages. Right? Except then you have the high cost and performance, which we don't want. So we have already talked a lot about just-in-time compilation. Just-in-time was a Japanese manufacturing technology that we adopted. The Java people adopted the term. Originally we called it, 1984, we called it dynamic compilation. And these guys had the problem. The computer that people had were something like a Sun workstation. And when you had the Smalltalk interpreter in there, it ran like 1/5 of the speed of a Dorado. So it's a 0.2 Dorados or something like that. And people didn't want that. So they said, can we do something to have almost the same performance or a even better performance than the Dorado on our Sun workstations? So they came up with the idea, the first time that you call the bytecodes, you don't interpret them. You call a special compiler that will translate the bytecodes into 68,000 machine language. Except that you can see here the problem. So the compiled code, the orange thing, is much smaller than the yellow thing. So compiled code runs so much faster than the interpreter. But since at that time you only had one processor, you actually took more time to compile and then to execute the compiled code than you would have interpreted anyway. So they actually wouldn't have too much gain. You can see that it's worse, right? Except now, he decided to execute the same code that he had already compiled once. So he saved that into a special region in memory, the compiled code cache. And then he noticed that he had already compiled again. So this last piece of code didn't call the compiler. So if you do that, if you run the same code over and over, then you come out ahead. It's faster. Now finally you had some workstation running at the same performance as one Dorado. And this was valuable enough technology that they spun off from Xerox and created a company called Park Place to sell this technology. So now one thing that would seem that you have, so since the processor is wasting its time compiling, you can't afford to spend too much time. Let's say, let it spend 3 milliseconds to compile that code fragment or something like that. You can't afford what these guys here are doing, where they spend like 12 hours to compile a piece of code. That's what we, and because of the JIT, we now have renamed this as ahead of time compilation. It used to be just called compilation because all compilation was like that. But now since we have different types of compilation, we call it ahead of time compilation. So, yeah, how can you compete? These guys have 8 hours to generate the best piece of code, and we have to do it in 3 milliseconds. So it seems that the JIT would always lose, except that what's a constant in a variable depends on several things. And one thing that it depends on is time. Here's a little graph. On the left, I put decades of time, and on the right, I put nanoseconds. So if you give it enough time, everything is variable. I mean, the processor, the Macintosh, it has an x86, but if you go back in time, it had a PowerPC, and then if you go back in time, it had a 68000. So the instruction set of your computer changes, the syntax of your language changes, everything changes. So with decades, there essentially are no constants. Now, if you narrow the time enough, for example, nanoseconds, I talked about the von Neumann bottleneck. So for one clock cycle, then there's exactly one word in memory that's variable. The rest of memory is all constant. So the problem is that the ahead of time compiler has to generate code that's going to be used for a long time. So it's going to be using, you generate a .exe file that's going to live on for 5 years, and it's going to go on this machine, this very other different machine. So it has, it sees lots of variables. So we go there between day and year. So it sees lots of variables. Whereas the dynamic compiler generates for this machine here, not that machine. It's generating code for this machine. And so it has access to lots of constants. And that's how it can at least not lose too badly to the ahead of time compiler. I'm not saying that it can beat the ahead of time compiler, but it can have a fair fight because it can have access to lots of constants that the other one doesn't. So this idea of the JIT, Craig Chambers was working on a very simple version of Smalltalk called Self programming language. It was originally called Smalltalk 86, and then was renamed Self. And the simplifications that they made to the language made it a lot harder to compile. So the implementation of a JIT was way harder than for normal Smalltalk. But he did a very good job for Self 1. And then he made a lot of improvements on the second version of Self. So you can see the orange pieces of code are much smaller. It takes a lot less time. So when he ran his benchmarks, he got to a number that we said 50% of compiled C code. So he'd take numeric benchmarks that are used for compare C, Fortran, and he ran self on them, and it ran at 50%, which is a really impressive number because it's checking for overflows, it's checking for array bounds, and doing lots of stuff, so it's a safe execution. So obviously it's never going to be 100% of the speed of C, but it was good enough. The problem is that his compiler was a lot slower. The problem, like I said, you have to do it in 3 milliseconds. He was doing suddenly in 3 seconds. So when you clicked on a menu, you had to hold the mouse for like 10 seconds, and then the menu would show up. And then you click it again, it was instant, because the code was so much faster, but it took a long time to generate. But some of the, I'm going to get back to how we'll deal with this, and that's the theme of this talk, adaptive compilation. But first I wanted to talk a little bit about Craig's work. So the idea that I have is that the computer wants to run Fortran or C, because that's what the guys that sat down, they are not designing a Smalltalk computer like I said yesterday, they're designing a C, a Fortran computer. And I want to program in Smalltalk or self. So how do we solve this conflict? It's interesting if whatever the language it improves upon, the compiler undoes. So for example, the language gives me dynamic types. So if I have x plus y, is x an integer, is it floating point, maybe even some other kind of object. So that's what the language, that's what I want. I don't want to have to declare types like in C or Fortran. So this is what the bulk of Craig Chambers' work is called type inference. He was able to look at the code and find out that for this particular plus, it's always going to be integer, never going to be floating point, never going to be anything else, right? So that's why those blue boxes, the compile times grew and grew, because this is a very hard problem, but he solved it. And you have generic code where you say x plus y, and this gets inherited by several different classes. And each one does something different. So you have very high-level code. So what the compiler does, he implemented something called customization, where if you have a method in an abstract class that then gets inherited by 4 different concrete classes, he actually generates native code, separate native code for each of the 4 cases. He doesn't have one bytecode method, one machine language. No, he has one bytecode and then one machine code for every actual subclass that actually uses this. And the advantage is that, for example, if you have self size, what's the class of self? Well, if it's in an abstract method way up in the class tree, then it's going to be different when I call that method in each concrete class. By doing customization, then suddenly the class of self is a constant in each of these custom versions of the code. So that's what he's trying to do. He's trying to take variables and make them into constants. So you have a very highly factored code. So instead of these huge methods, you break them up into tiny little methods. And so the compiler will do inlining. So when it knows that the class of self is constant, then it doesn't even compile a message send. No, it will go to the actual method and bring the code there and put it into place. And once that code has come into place, and he can only do that because he has customized things, then he can do lots of further optimizations. So that's why I said yesterday that when they ran benchmarks, it was as if they were taking a negative number of clock cycles to send a message. Because if you don't take into account customization and inlining, it seems magic because, well, you do the math, how many messages were sent? But the messages weren't sent, actually, in the machine language. And you have polymorphism, where you send the same message to many different types, whereas in Fortran or C, you'd have the switch case thing to explicitly test for each different type and do something differently. So we have something that we'll see right after this called the polymorphic inline cache, which is a switch case system that the self-compiler will just add to your code, so compensate for that. So what's interesting is that most of the code has no effect on execution time. Like 80% of it doesn't, it's initialization code or whatever. Just 20% of your code is responsible for 80% of the execution. So I suggested to the self people, why don't you take the self1 compiler and compile almost all code and then measure, and if it's one of the 20% of hotspots that we call it, then you call the fast compiler. So this is adaptive compilation. You spend time on code that's worthwhile, that will give you results. And you use very simple compiler, generate bad code for code that, you know, really doesn't make much of a difference. You just have to run it a little. So when I suggested this, then Urs wrote back and said, guess what our next paper is about? Because we've been working in exactly this technology. Except that he had added a different feature in which he actually extracted information, type information, from the execution of the bad code. And I'm going to show how that was done. And so he made the second compiler, the advanced compiler, also fast, because it didn't have to do the costly type inference. The result isn't 100% as good as type inference, but it's good enough. And then the second compiler was also fast because it had type information that was accumulated by running the first code. So this is basically how it works. You start with the source method. Then when you first execute, you generate unoptimized code, but then you have some counters. Every time you execute, you increment a counter to see if it's a hotspot or it isn't. And if it's executed very often, then you translate it into optimized code. And then sometimes you get a bug and then you call it the debugger. The problem is that the fancy code can't be understood in terms of the debugger because the code is rearranged. So what it does, it has what we call dynamic de-optimization, where the optimized code is translated back into the unoptimized code, which can be debugged single step. And he has to map the stack from one to the other one, the state. So it's it's very complicated technology, which is why after 25 years it's so rarely used, because, you know, it's a very high engineering effort. And at the bottom, you had the Deutsch Schiffman thing introduced something called the inline cache that I'm not going to go into, but basically you have a bunch of code and suddenly you have the equivalent of a send message. It will generate a little switch case thing. So is the class this? Then jump here to this compiled method. Is the class this? Jump here. And if it's not any of the classes that you've seen before, then you extend the pick. So after running for a little while, if you look at the pick, you know for that call send sites that we call, the send site, what kind of classes that you've seen. So that's the equivalent of the inference. So in the open Smalltalk VM by Elliot Miranda, they're trying something a little different. Clement is trying something called Sista, where they'll translate the bytecode to machine language. It's just one compiler, but then he'll translate code that's used a lot from one bytecode to another bytecode that will allow the compiler to generate better code. And they hope to have much higher performance. And there's a related technology to all this that I've been talking about, which is called partial evaluation, where you take a program and you declare that some of its inputs will be constant. And then you generate a second program that's more efficient, where these things are always constant. And if you have that information, in theory, you could take an interpreter and use this partial evaluation tool, which is really hard to write, and then you could get a compiler out of it. You could get a JIT without ever having to write a JIT, which is a problem that people want. So the PyPy people tried to write Python in Python, and they started with the partial evaluation scheme, and then they moved on to something different. And then there's the Growl, Truffle people, and you write an interpreter for the abstract AST, and then it'll try to do partial evaluation to give you a JIT. So I hope that this gave you a good idea.
No questions? Okay, thank you, Jecel.